Hello, welcome to the course PH5 BO6 Electrodynamics 2. The contents of today's lecture is taken from a textbook of electrical technology by B.L. Tereja and A.K. Tereja. We'll continue to discuss topics from chapter 2, network theorems. What's a constant voltage source? So constant voltage source is a voltage source which provides constant output voltage irrespective of the changes in the load current or load resistance. Typically, an ideal constant voltage source should have a zero internal resistance. So what happens when you have zero internal resistance? The internal potential drop is zero. So whatever is the potential of the power supply, the entire potential is going to drop across the load resistance irrespective of the value of the load. But there is nothing called an ideal constant voltage source, because in practice every voltage source will have some finite amount of internal resistance, some non-zero value for the internal resistance. So in practice, you can never achieve an ideal constant voltage source. The only thing you can make sure is that the internal resistance of the voltage source is very, very low, so that you can approximate it to an ideal source. Let's now quantitatively analyze how does minimal internal resistance ensure constant output voltage. Let's consider a battery of 6 volt EMF which has an internal resistance of 0.005 ohm. So this is a very small value. Okay. So initially when the circuit is open, so basically there is no resistance here, you keep these two terminals open, then the output voltage is going to be whatever is the voltage from the source. The 6 volt is going to drop between the points A and B. Now you short circuit this using a resistance here, and by choosing an appropriate value of the resistance, suppose if you manage to get a load current of 10 ampere. Now what is the internal drop now? The 10 ampere current is going to flow through the load resistance as well as the internal resistance. So the internal drop is going to be current 10 ampere multiplied by internal resistance 0.005 ohm, which is 0.05 volt. So out of 6 volt, 0.05 volt drops internally, and the remaining 5.95 volt is going to drop across the load resistor. So if you look at the current has varied hugely from 0 ampere to 10 ampere. There is a huge variation in the load current. But if you look at the output voltage, the voltage has changed only from 6 volt to 5.95 volt. So compared to the change in load current, the change in the output voltage is negligible. That's why when you have a very small internal resistance, you can approximate your voltage source as a constant voltage source. Similarly, what is a constant current source? As the name suggests, it is a voltage source which provides constant load current irrespective of the changes in the load resistance. An ideal constant current source should have infinite internal resistance, so that irrespective of the changes in the load resistance, the value of the current is going to be constant. So if the internal resistance is much higher than the load resistance, what happens is the changes in the load resistance will be masked by this huge internal resistance, so that you have an almost constant current through the circuit. But as I said in the previous case, there is nothing called an ideal constant current source, because for no practical voltage source you can have infinite internal resistance. So the only thing you can do is keep the internal resistance much higher compared to the load resistance, so that you can approximate your current source as a constant current source. Once again, let's numerically analyze how does a high internal resistance ensure constant current from the source. Once again, let's consider a 6-volt battery which has a huge internal resistance of 1 mega ohm. Assume that you are varying the load resistance from 20 kilo ohm to 200 kilo ohm. Let's now calculate what is the current from the source corresponding to these two load resistances. For 20 kilo ohm resistance, the current from the source is total voltage, which is 6 volt divided by total resistance. You have the internal resistance and the load resistance connected in series. So total resistance is summation of these two. So you have 1 mega ohm plus 20 kilo ohm, which is 6 divided by 1.02 into 10 to the power 6, which is around 5.9 microampere. Whereas in the case of 200 kilo ohm load resistance, the current through the circuit is 5 microampere. So if you look at the variation in the load resistance, it changed from 20k to 200k, almost 10 times the load resistance has changed. But what is the corresponding change in the current from 5.9 microampere to 5 microampere? The current has changed only by 0.9 microampere, 0.9 into 10 to the power minus 6 ampere. So even though the resistance has changed hugely, the change in the current is negligible. That's why whenever you have a very high internal resistance, the source can be approximated as a constant current source. Moving over to the next topic, superposition theorem. As we have discussed yesterday, this is one of the direct methods used to analyze a complicated network. Superposition theorem pertains to linear resistances or impedances. What do we mean by a linear resistance? So in linear resistance, there is a linear relation between voltage and current. In other words, voltage is proportional to current. If you look at the Ohm's law, V equal to IR, here is voltage is proportional to current, and resistance is nothing but a constant of proportionality. So this is what we mean by a linear resistance. There are also nonlinear resistances where the linear relation between voltage and current doesn't hold good. So it's a nonlinear relation, which means the resistance is no more a constant. So in the case of nonlinear resistor, the value of resistance changes as a function of the current. So according to superposition theorem, in a network of linear resistances or impedances, usually for DC network we use resistance, and for AC network we use the terminology impedance. So in a network of linear resistances or impedances containing more than one generator or power source, the current which flows through any point in the network is the sum of all the currents which would flow through that point if you consider each generator or power supply separately, while replacing all other generators with their corresponding internal resistances or impedances. So in a multi-generator network, the total current is nothing but an algebraic sum of individual currents which are measured while keeping one generator at a time and replacing all other generators with their internal resistances. So we'll first prove the superposition theorem, then we also do one example problem so that you will be clear about the information as well as methodology of this theorem. So let's consider a representative network here which consists of two AC sources V1 and V2 with internal impedances small z1 and small z2. Network consists of three external impedances, capital Z1, Z2 and Z3. We have two closed paths here, one including V1, Z1 and Z3, second one including V2, Z2 and Z3. So first one I call as loop 1 and second one is loop 2. Let I1 be the current through loop 1 and I2 be the current through loop 2. For analyzing any network, we can use the fundamental Kirchhoff voltage law. So let's apply Kirchhoff voltage to loop 1 in the clockwise direction. So remember, if you are moving in the direction of the current, then the potential drop is negative. If you are moving against the current, the potential drop is positive. Okay. So you start from the power supply here. It has an internal resistance Z1. So when current is flowing in the clockwise direction, you are also moving in the same direction. So the corresponding potential drop is minus I1 Z1. Similarly, for capital Z1, you are moving in the direction of the current. So potential drop is minus I1 Z1. Similarly, you have minus I1 Z3 here. But for Z3, there is another current I2 which is flowing in the opposite direction. Right? So in that case, the potential drop is plus I2 Z3. So you can combine these two and write minus I1 minus I2 into Z3 plus the EMF V1 equal to 0. You can rearrange the terms, get all the power drop to the other side. You get I1 Z1 plus I1 Z1 plus I1 minus I2 Z3 equal to V1. Now, if you are considering a very good voltage source, almost like an ideal voltage source, then we know that its internal impedance is negligible. So for all practical purpose, you can approximate Z1, small z1 to be 0. Then your equation gets modified as I1 capital Z1 plus I1 minus I2 Z3 equal to V1. Clubbing all the I1 terms together, you get I1 into Z1 plus Z3 minus I2 Z3 equal to V1. This is equation 1. Same way, you can write down Kirchhoff voltage law for loop 2. So you start from the power supply, you have minus I2 Z2 and minus capital I2 Z2. Then you have minus I2 minus I1 into Z3 plus V2 equal to 0. You have an almost similar equation here. Once again, you can consider that the internal resistance or impedance is negligible. So Z2 you can approximate to 0. Then you get a similar kind of equation, just that instead of I1 you will have I2. Instead of Z1 you will have Z2. Similarly, instead of V1 you will have V2. So the corresponding equation is I2 Z2 plus I2 minus I1 into Z3 equal to V2. You can club the I2 terms together. You have I2 into Z2 plus Z3 equal to minus I1 into Z3 equal to V2. This is equation 2. So this is the current through the circuit when you consider both the voltage sources. Now we have to prove that this is equal to the sum of the individual currents. Okay. So let's first remove V2 and assume that the network consists of only one voltage source V1, and V2 is replaced by its corresponding internal impedance Z2, and we know that for all practical purpose Z1 and Z2 are 0. Let I1 prime be the current through loop 1 and I2 prime be the current through loop 2. You can apply Kirchhoff voltage law to loop 1, follow the same procedure, then you get a similar equation, just that instead of I1 you have I1 prime and instead of I2 you have I2 prime. So for loop 1 equation is I1 prime into Z1 plus Z3 minus I2 prime into Z3 equal to V1. When you apply Kirchhoff voltage law to loop 2, remember V2 is removed now. So in place of V2 you have 0. So the equation is I2 prime into Z2 plus Z3 minus I1 prime into Z3 equal to 0. So these are equation 3 and 4. Similarly, now you can replace V1 with Z1 and reinstall V2 here. Once again, remember Z1 and Z2 equal to 0. In this case, current through loop 1 is I1 double prime and current through loop 2 is I2 double prime. So you get a similar kind of equation, just that the prime notation is replaced with a double prime notation. So I1 double prime Z1 plus Z3 minus I2 double prime Z3 equal to 0. The right hand side is 0 because V1 is removed now. So this is 0. V2 is back. So for loop 2 on the right hand side you have V2, on the left hand side you have I2 double prime Z2 plus Z3 minus I1 double prime Z3. So these are equation 5 and 6. What you do is you add equation 3 and 5, you get I1 prime plus I1 double prime into Z1 plus Z3 minus I2 prime plus I2 double prime Z3 equal to V1. Similarly, when you add equation 4 and 6, you get I2 prime plus I2 double prime into Z2 plus Z3 minus I1 prime plus I1 double prime Z3 equal to V2. You can compare these two equations with equation 1 and 2. So for both the equation, on the right hand side you have V1, so you can equate these two. Similarly, for these two equations on the right hand side you have V2, which means you can equate this with this one. So you have I1 prime plus I1 double prime Z1 Z3 minus I2 prime plus I2 double prime Z3 equal to I1 into Z1 plus Z3 minus I2 into Z3. So if you compare the terms you have similar terms on either side, which means you can equate the coefficients. So when you equate the coefficients of Z1 plus Z3, you get I1 prime plus I1 double prime equal to I1. Similarly, when you compare the coefficients of Z3, you have I2 prime plus I2 double prime equal to I2. So what is I1 prime and I2 prime? This is the individual current when you consider only V1. Similarly, I1 double prime and I2 double prime are the individual currents when you consider only V2. So you have proved that the sum of the individual current equal to the total current. Let's do a quick problem based on superposition theorem. So using superposition theorem, find the current flowing through resistance R shown in the figure. You can neglect the internal resistance of the cell. So we have three resistances, R1 equal to 0.05 ohm, R2 equal to 0.04 ohm, then resistance R equal to 1 ohm. And this is a multi-generator network. You have two batteries, one with voltage 2.05 volt and another with 2.15 volt. So you are asked to calculate what is the current through the resistance R. So according to superposition theorem, the total current is nothing but an algebraic sum of the individual current. So first you can remove E2, replace it with its internal impedance. We are asked to neglect the internal impedance, so you can just remove this one and connect the terminals together and calculate what is the current. Similarly, you remove E1 and calculate the current, then find out the sum of these two current. That will give you the total current. So first I am going to remove E2. This is the corresponding circuit now. Now if you look at this circuit, look at these 2 points A and C, you will find that the resistance R2 and resistance R, these two are parallel, right? So I can calculate what is the parallel resistance between A and C. I call it as RAC. This is 1 parallel 0.04. So its value is 1 into 0.04 divided by 1 plus 0.04, which is 0.038 ohm. Now RAC is now in series with R1. Right? So 0.038 is in series with 0.5 ohm. So the total resistance experienced by the battery E1 is nothing but 0.05 plus 0.038, which is 0.088 ohm. So you have 2.05 volt connected in series with the net resistance 0.088 ohm. So the total current drawn from the battery is voltage 2.05 volt divided by total resistance 0.088 ohm, which is 23.3 ampere. As I said, the parallel resistance RAC is in series with R1 here. In the case of a series connection, current is a constant. So you have 23.3 ampere flowing through R1. Similarly, 23.3 ampere flows through RAC. So current through RAC is 23.3 ampere. Now what is the voltage across RAC? Voltage is nothing but current multiplied by resistance. So this is 23.3 ampere into 0.038 ohm, which is around 0.896 volt. So you have 0.896 volt dropping across RAC. RAC is nothing but a parallel combination of R2 and R1, and we know that in the case of parallel connection, voltage remains a constant. So 0.896 volt drop across R2, the same 0.896 volt is going to drop across R as well. So the current through the resistance R is nothing but the voltage 0.896 volt divided by the corresponding resistance, which is 1 ohm. So current through resistance R, we call it as I1. This is 0.896 ampere. So same way, now you can remove E1, reinstate E2 and calculate what is the current through the resistance. Follow the same procedure. Now you can see, if you look at the terminals A and C, R1, which is 0.05 ohm, and R, which is 1 ohm. These two are parallel. So RAC is now 1 parallel 0.05, which is around 0.048 ohm. Now this RAC is in series with R1, which is 0.04 ohm. So the total resistance experienced by the battery is 0.088 ohm. So the net current from the battery is total voltage divided by total resistance, which is around 24.4 ampere. So this is going to flow through RAC. So the potential drop across RAC is voltage multiplied, current multiplied by resistance, which is around 1.16 volt. So the same voltage is going to drop across 0.05 ohm, and the same voltage is going to drop across 1 ohm, because these two are in parallel, right? So current through 1 ohm, we call it as I2. This is voltage 1.16 volt divided by 1 ohm. This is equal to 1.16 ampere. So the individual currents are 0.896 and 1.16. So according to superposition theorem, the total current is an algebraic sum of these two. So you get total current is 2.056 ampere. So this is how you analyze a network using superposition theorem. That's for today. In the next class, we will learn about Thevenin's theorem and also understand how to analyze a complicated network using Thevenin's theorem. Thank you.